Hello everyone, welcome to our presentation. First of all, let me thank the organizers of this conference. As you can see on the screen, our paper is proposing a strategy on generating high-resolution adversarial images, if I simply put. This is a first product of our continuous work. We are Professor Frank Laprovost, I Ali Osman Topal, Elmir Avdisunovic, and Raluca Kitik. Image recognition and classification is such a task, humans can do it effortlessly. However, when it comes to classifying billions of images, humans need time, days, weeks, even months. Thanks to new developments in machine learning algorithms and resources, of course, especially on CNNs, this task can be done very quickly and accurately. That's why CNNs are now at the heart of many applications that make our lives easier, like facial recognition, voice recognition, self-driving cars, robotics, and so on. However, in the wrong hands, CNNs can be used to invade our privacy. For instance, millions of photos can be scrapped from public websites and social media platforms without the owner's consent to train some CNNs that empowers facial recognition systems. Moreover, photos may contain information about places, events, and relationships with family members or friends, which poses a threat to safety of others. Second cons, we can say that even CNNs are so powerful, they are still vulnerable to adversarial attacks. Indeed, adding appropriate noise to an input may cause a CNN to result in a different response, as we can see in this sample. The consequence of these attacks can be devastating if the intent is malicious. Special designed glasses can lead CNN to misclassification like the one in this example. So this is how criminals can escape facial recognition security systems. Or adding some patches to a stop sign may cause CNN to recognize it as a speed limit 45, and we can imagine the consequence of that. It seems there is still room for improvement in terms of robustness. Here we can see some sample of attacks. First row is the clean images, second rows are the adversarial images. We can see that adversarial images have some artifacts the human eye easily distinguish them. This is one sample of our attack, which is we can see that the differences are indistinguishable by a human eye, even though CNN recognizes the adversarial one as altar. We can categorize these attacks as black box, white box, targeted or untargeted, and more or less visible. Black box attacks, the attacker doesn't have any information about the CNN. However, in white box attacks, attacker has access to the CNN parameters architectures and use those information to create the attack. Targeted attacks, the attacker enforces CNN to get the image classified as a specific target class. However, in untargeted attacks, enforces the CNN to misclassify the adversarial image any category different than the true class. The most challenging one among all these attacks are the black box, targeted, and unnoticeable one. This is what we aim in our previous works. This diagram summarizes how adversarial attacks work. We have original clean image with high resolution domain. We scale down to the CNN input size, then algorithm creates some noise, we combine them and then send to the CNN. CNN decides some label values and then algorithm checks if it is satisfying, stop, otherwise algorithm will keep generating adversarial noise. The end product of these attacks, in classic adversarial attacks, will be 2 to 4 times 2 to 4, which is the CNN input size. It means the classic adversarial attacks can generate with the maximum size of CNN input size. One way generating high-resolution adversarial image is the direct attack. This diagram summarizes it. We start with the original image. Algorithm this time works with the adversarial noise. It is as big as original image. Combine them, scale down to the CNN input size, get the label value. If it is not satisfying, keep working on the adversarial noise. So there are three main challenges here. First one is speed, second adversity, then visual quality. Speed, we can see that now the algorithm is working with the largest search space. Before it was 2 to 4 times 2 to 4, now it is around 86 times larger. So it is going to take time to algorithm to find out which pixels to manipulate. Adversity, when we scale down to the CNN input size, we don't want to lose an adversity here. And the last one, visual quality. This adversarial noise, when we edit the original image, it shouldn't create some artifacts that can be seen by the human eye. We have done this test in our machines. We let it run around 2 days. At the end, the results were not satisfying at all. So this direct attack is kind of failed. Our contribution in this conference paper is a strategy that offers any existing attacks to work on a low resolution domain but generate high resolution adversarial images. We have tested this strategy in our feasibility study with 10 high resolution images on one CNN and by using one attack. Here is the summary of our strategy. We start with the original image, scale down to the CNN input size, and then attack work on the image, generate adversarial image, and you can see that it is working on the low resolution domain. We scale up to the original size, which is going to be our adversarial image after this process finish. And then we have to scale down and have a look what CNN says about that image. Then if it is not satisfying, attack the algorithm. We'll keep working on that one. Here we need to check the L2 distance between original image and adversarial image, how similar they are. And then we like to say the loss, scaling up and down, how much confidence level we are losing here. So interpolation techniques play a very important role in our strategy. When scaling down the image, lots of information will be lost. And during scaling up the image, the interpolation technique should recover the lost information as much as possible to have the same quality with the original image. So this strategy depends on the quality of these interpolation techniques a lot. To test our strategy, we picked 10 high resolution clean images. And as a CNN, we use VGG16, which is trained on ImageNet. And as an attack, we picked a black box targeted attack based on evolutionary algorithm. Here we can see the size of the images and what VGG16 says about that images and their confidence level. The last row represents the target categories we ask our attack to convert those images. Here we can see one sample, the original image and the adversarial image at the end we have created. They are with the same size. The original image is classified as a comic pic with the label value 0.49, and the target adversarial image is classified as an alter, which was our target category, with greater than 0.55 confidence. It took less than 1 hour in our machines to generate such images. When we compare with the direct attack, this is very fast, we can say. So the conference paper gives all the information about the loss function, L2 distances, what kind of interpolation techniques we tested and which one is the best one in our case, and how EA-based attack works, and performance of our strategy, at least for one attack, timings, number of generations, convergence characteristics, and etc. Here we can see the visual quality of our high-resolution adversarial image. The first one is a clean image, second one is the adversarial image. We can see here the high-frequency informations, but in the adversarial image, they are lost. It is not because of our strategy, it is because of the interpolation techniques, which are not good enough to preserve these high-frequency information. Even when we test this one with the clean image scaling up and down, we got the same results. Conclusion. So, as far as we know, this paper provides the first effective theoretical and practical attempt to creating adversarial noise of the size of the original image. So our strategy can be used for any attack. It will help to any attack to work on the low resolution domain to generate high resolution adversarial images. And it takes less than 1 hour to generate such image. So meanwhile, we extended this work and we tested on 10 well-known CNNs, and the results are published in the Journal of Information and Telecommunication last month. And this work led us to a lot of future works. In fact, we have seen that we can simply increase the quality of our high resolution adversarial images by getting rid of this blurriness. We came up with two different techniques and we are still working on that one. And we are still working on the speed of this attack. And the results are promising, and hopefully we are going to present them in the next ACIDS conference. Thank you very much for your time.